Hey there, this is Horner, and this is 1991 Physics C Mechanics question number one. And we've got a massless spring. So notice it is massless, which is really weird, but it does not have any mass. It has a force constant of 400 newtons per meter. It is fastened to the left end of a vertical wall, so we see that it's attached to the wall. Initially, block C, here's our block, and block D rest on a horizontal surface with block C in contact with the spring and touching D. We go ahead and push it back, and in figure 2 you'll notice that it is now moved to the left and it compresses the spring by 0.5 meters. So the first thing they want us to do is determine the elastic energy stored in the compressed spring. So pretty easy to do, shouldn't be anything that's very difficult. There's no calculus involved. This is just U is equal to 1/2 kx squared. So pretty straightforward and simple. This is equal to 1/2. They told us the K value is 400 newtons per meter. And our stretch here is 0.5 meters. It's compression. As long as we go either in towards the spring or stretch the spring out from equilibrium, then we can call that a stretch or compression. And so if you do this math, you should end up with 50 joules. Points here, 1 point here, 1 here, and 1 here. Alrighty, so let's go ahead and take a look at the next part. For part B, it says block C is then released. So when we let go of this, it accelerates to the right. So we know that our direction of motion, we're going to call positive in that direction. It gets towards block D, the surface is rough, so we know that there's got to be friction, and the coefficient is 0.4. Because it's moving, this has got to be a coefficient of kinetic friction. The two blocks collide, they stick together, so that means that it is an inelastic collision, and they move to the right. Remember that the spring is not attached to block C, so it can let it go, and they want us to determine each of the following. So the first thing here is the speed Vc of block C just before it collides with block D. We're going to go back and use kinetic energy again here. So we know that kinetic energy is equal to 1/2 of the mass of block C times the velocity of block C squared. And that the work here done by friction is equal to the force of friction times the distance or the change in position that that friction acts. Remember, the force of friction is equal to the spring constant times the force normal. So that's the normal force acting on the block, and then we're going to multiply that times the distance that it acts through. Our kinetic energy here then is going to be equal to the potential energy of the spring minus the work done by the friction. So that's how we can account for friction here. We said earlier that kinetic energy is 1/2 of the mass of the block C times the velocity of block C squared. That's going to be equal to the potential energy that we have minus, and then we said that this is mu times, now we've got to figure out what is the normal force. So for this block, we know that straight down is mg and straight up is the normal force. And because the sum of the forces are equal to, sum of the forces are equal to 0 for the block, since it's not moving up or down, then that means that Fn minus mg is equal to 0, and that means that Fn is equal to m times g. So here we have mass of that block C times gravity, and then we can multiply times the distance that it travels. So let's go ahead and solve this whole thing for Vc. So this is going to be Vc squared is equal to the potential energy minus mu times mc times g times d. We're going to multiply the whole thing times 2. So I'm going to take this times 2, and then we've got to divide the whole thing by mc. So when we do that, we can now go ahead and plug in Vc. That's equal to the square root of, let's go ahead and put all of our numbers in. This is going to be 2 over 4, 2, and then 4 kilograms we know is the block C. Potential energy here, they told us, was 50 joules. And where did we get that number? If we go back up, you'll see that's what we calculated earlier. for the spring energy. So really we could put S here for each one of these being spring energy. So it's 50 minus, and then we've got 0.4 for our coefficient of friction. We're going to go ahead and extend the square root over, times the mass, which is 4, times gravity, which is 10, and then the distance it travels is 0.5 meters. So remember it was compressed 0.5, so it's going to extend out for 0.5 until it comes all the way through. So that should be a lot more helpful. Alrighty, so now that we've done that, we can go ahead and we can plug everything into the calculator, and you should get 4.58 meters per second. So where do you get all of your points? Okay, so first thing we need to do is we need to recognize that we have conservation of energy. So where do we end up with that conservation of energy? This equation will give us the conservation of energy. You get 1 point for finding the kinetic energy equation for the block. You also then get the energy of, well, you get the work dissipated by friction. So if you include it, you get a point for it. Then we get a point for having this equation where we filled everything in terms of just our variables. You've got to solve, and once you solve and you get you get a number, final answer, that's worth a point. So physics, 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 4 points for physics, 1 point for actually doing any calculations. If we go to part C, it says the speed VF of blocks C and D, and you can do this just after they collide. So first thing we need to do is think about, well, what kind of collision is this? Because they are sticking together, we know that this is a inelastic collision. In inelastic collisions, the mass of C times the velocity of C plus the mass of D times the velocity of D before the collision should be equal to the mass of C plus the mass of D after the collision times the final velocity, and that is the same for both. We know that this is equal to 0, and so now we're going to solve for the final velocity. So our final velocity should be equal to the mass of C times the velocity of C divided by the mass of C plus the mass of D. Let's go ahead and plug everything in. So now at this point we've got 4 kilograms for the mass of C. We said earlier the velocity of C was 4.58 meters per second. We're going to divide that by our two masses, which is 4 plus 2. And once you find your answer for VF for the two blocks together, that's 3.05 meters per second. So where do we get our points? This basically just says that's the conservation momentum. Once we have solved for VF, there's a point there. We substitute everything in and get an answer. So physics, physics, and calculation. Next thing it says is the horizontal distance the blocks move before coming to rest. So that is just at the point where they're going to come to rest. So here we go. Let's go ahead, and we know that the change in kinetic energy here should be equal to that work, the change, well, it's actually just the work done by that frictional force. And because when we use all of that kinetic energy, then we know that it's going to stop. So how does that kinetic energy get used up? It is the work done by that frictional force. So let's go ahead and do our equation again. 1/2 of the mass times the velocity squared. So before they come to rest, we know that this mass is the total mass. It's mass of block C plus mass of block D times the final velocity squared, and that is equal to the work done by the friction. So that is mu times the mass of both blocks, mc plus md, and then we're going to multiply that times gravity, and then finally times d. So remember, this is mu times the normal force times the distance that it travels. So if we wanted to, we could say that this is the kinetic energy before is equal to the work done by friction after. And so let's go ahead and plug everything in. First thing we want to do is solve for D. What's really nice about this is we can get rid of the mass, so the mass won't matter. And then if we solve for d, we're going to divide both sides by mu times g. So this is mu g. So now we're going to have d is equal to v f squared all over 2 mu g. Now that we know what our equation is, so basically this 2 here, we've got mu g on this side, we've divided both sides by mu g, so that's why we end up with what we do, because we're looking for d. And so now we just got to go ahead and plug everything in. So our final velocity we know is 3.05 meters per second, but we got to square it, and we're going to take that divided by 2 times our coefficient, which is 0.4, and then gravity, which is 10 meters per second squared. And if you do your math, you'll end up with 1.16 meters. So where do the points come from? For this one, there are 3 points. One of them is just thinking about this kinetic energy going into work. And then next thing they want you to do is go through and use this equation to get this guy. So physics, physics, and then our math. And that is all of the points almost for this. They gave one more point because they only had 14, so they needed one more point, and that is if all of your final units are correct. So all units need to be correct. And how do we know that all those units are correct? We have to just find them all. So meters here, meters per second for this one, meters per second for this one, and then joules for this one. So as long as all those units are correct, you get that last or 15th point. And that is the end of this question.